Good afternoon, everyone. My name is Reza Rahani. I'm a student of Ryerson University. Today I'm going to present you the collaborative robots for rescue missions. So for agenda, I'm just going to tackle a few things. I'm going to start with introduction to eco-positioning. I'm going to move to mathematical approach, then simulation using MATLAB, hardware structure, simulation and testing in lab center product use, and the implementation. And at the end, I'm just going to wrap up with conclusion and future work. So as you know, the radar positioning widely used in commercial and military, known as GPS. This satellite positioning has the accuracy of the 1 meter. However, eco-positioning, which applies the same concept of this satellite positioning, but with better accuracy. The accuracy that I'm talking about is about 1 centimeter. And therefore, for the robotics applications, this is very interesting to apply. You can also think about other applications for workers working on the underground environment, such as tunnels and So they are exposed to high level of hazardous environments, and to rescue them because of the high temperature, poisonous gas, and also electrocution. So it's very, we as a human, we cannot really rescue them properly. So here, again, robots can be very efficient. And also another application can be removal of the object from the path in order for the safety. So the objective here is to design the eco-positioning framework for robots to detect their positions, and also to create multiple robots which collaboratively work with each other to detect the object in the field. And also another criteria is to avoid any collision of the robots with the any other robots or with the borders of the field. So here I'm just gonna talk about the mathematical background. This is very simplified scenario that we have 2 transmitters here. So each of them are generating the ultrasonic sensors. And the intersection point, which is the receiver, this is the point of the interest. We want to exactly know what is this point. So we already know the position of the transmitter. We know XA, YA, and XB, YB. These are the knowns. And the distance from this point with respect to the transmitter can be calculated by T1 times Vs. Vs is the speed of the sound through the air, and T1 can be measured through some calculations. So these are the formula. It is the system of nonlinear equation. So the interest again here is to find the x and y, which is the coordinates of the robot. So in order to solve these equations, we should define 2 more parameters, k and d square. I'm just going to explain it later. And then we can just substitute every values here and to determine x and y. So RA and RB is the distance from the intersection point to the center of the circle, and D is the distance between the 2 circle center, and K can be defined as the area under the triangle of the with the vertices of 2 center of the circle and the intersection point. So, but it is not very simple here because we want to increase the accuracy. So in order to increase the accuracy and measuring, reducing the noise, we need to have more ultrasonic sensors as base stations. So the ultrasonic sensors are located at the corner of the field, and the location is known. So here, what I'm doing here is comparing every 2 circles, as I explained in the previous slide, in order to determine this location of the intersection. So A and B are any combination of these 2 And by substituting these values into the previous equations, we can derive 4 different points, and then by averaging all of them, we can estimate the locations of the robot. So this is the block diagram using MATLAB. So the first step is to simulate all the signals that we have, and then combining the signals with the adding noises. So as you can see here, these are all generated signals, and then the next step to this block diagram is to pass all the signals to the receiver. So here we are detecting the signals, and then we pass it through the echo positioning mathematics. So in order to do that, we need to first convert all of the signals, which are the time, in order to distance, in order to estimation of the point. And again, the method is explained before. So it's very simple after converting all to the distance, and then as I explained, we can get the estimation point. And the whole block diagram can be expressed as ultrasonic framework model, which the input is the actual point and the output is the estimation point. And we are feeding the actual point in order to calculate the error of the system. Okay. So again, we have ultrasonic framework model, we have actual and we have estimation point. The estimation points goes to decision making. Decision making is when robot decides whether it detects any object or detects the ball, and then all the signals goes to updating update robot position. It actually simulates the movements of the robot, and then at the output we can visualize everything, and also we can visualize the estimation point. So here is the visualization. Again, in the MATLAB, the algorithm is written like this. The first step is to create a robot. The second one is to initiate its position and the movement. And the third one is the estimation of the position, as I explained it before. And then movement decision, updating the display, and check for borders. So within this field, this is the robot, and as you can see, this is the track of the movement. So the robot is moving inside the field, and this is the plot for the error with respect to time. The error is between the actual point and the estimated point. So now this is the visualization for 2 robots. The algorithm is pretty much same, but with more updating. It also again creates and initiate 2 robots, checking for the borders and collision, and check for the detected object. And if it detects the object, it's supposed to send the positioning to another one. And again, for each of the robots, the errors is plotted here. So now about the structure of the hardware, I divided into 4 parts. The first part is the ultrasonic sensor, the transmission. The second part is the receiver transmitters. Third part is the signal detection, and the fourth part is the processing unit. So for the transmitters, so this is the ultrasonic transmitter. So these are again those 4 base stations that I was talking about. These are the transmitters. At the beginning, I was trying to put 1 transmitter here for each station, base station, but I realized that the coverage is not good enough. So that's why I increased the transmitter in order to increase the view angle of each transmitter. So right now, for each base station, we have 3 transmitters with the 45-degree difference. For receiver sensors, so as I said, each transmitter has the view angle of 45 degrees. So in order to coverage of 360 degrees, we need to have 8 sensors for receiver point. So on the bottom right is the actual one, and this is the theory behind that. Okay, now it's about signal detection. After understanding the receiver and the transmitter, so this is the board that I just saw there. So every signals that coming from the receivers. So it goes to the thresholding point. The thresholding point is actually quantizing the signal. And then it passes through the RC filter, which is low pass. And then all the signals goes to OR gate to like getting the output pulse. So this is the board. I used some amplifiers, some components, as you can see, some OR gate. So the next one. In order to process and to do the decision making, the DSP33 is chosen. So after the detected pulse goes through the microcontroller, it goes through the interrupt input, and then on the output, it creates 6 different PWM pulses, and all the PWM pulses goes to DC motor, and the proper signals goes to the right or left-sided motors. And on the other hand, the ZigBee communicating with the microcontroller and sending the positions to UART serial communication port, and also the position of another robot can be sent within the ZigBee. So after implementing and simulating all the signals with the MATLAB, we need to convert everything and add more within the Proteus in order to program the microchip, the microcontroller. So here we get the position of the robot, we simulate all the signals, and then we send all the signals through the serial communication port to the Proteus. And the Proteus, it receives the signals and then calculate the actual positioning in the C program in order to program the microcontroller. So this is the screenshot for the Proteus. So all the signals from MATLAB sent to serial port communications, and then it goes to simulation for detected pulses, and then it goes to the upper unit, which is Proteus positioning processing unit. And the core and the most important unit is that one because it's supposed to calculate the positioning of the robot. So this is the main idea. So this is the MATLAB. In this example, the X location is -45 and Y is 15 centimeters. And this is the one port. All the information, all the signals passes through the visual serial port and sent to Proteus. This is the Proteus, and the output can be seen as this one. As you can see, the error is not very much. It's very good actually estimation. We can compare the result. The actual one is that one, and this is the estimation. So for implementation, I use the microchip MPLAB to implement all the programs, and for the DSP, in order to get faster operations, I use DSP33, which is this one, and this is the board of the M33. The good thing about this board is, first of all, it has this kind of processor. It supports that, and it also has the motor drive module on that, which is very good. We don't need to add extra unit to that in order to make the robot move. So the conclusion is, first of all, MATLAB help us a lot in order to verify the design and verify the mathematical derivation. And also Lab Center was very helpful. In order to programming the microcontroller. And the result is echo positioning. As I said, we did it just for the one robot, and it was perfectly working. I think I can show the video to you at the end if I have time. And the actual accuracy is just within the, some centimeters. This error is very good actually, which is more accurate than the other approaches that some other people did. For the future work, we can do three things. First of all, we can improve the accuracy of the system. We can improve the system by adding more IR sensors. And it is actually, we are doing synchronizing this system. So obviously, by adding more sensors, we can gather more information from the environment, so we can increase the accuracy as well. And also, the third option is to use the Bluetooth wireless pattern in order to communication. Right now, I'm using this ZigBee module in order to communicate. So in the future, we can replace it with Bluetooth wireless. So these are the references. And any questions?
Okay, thank you very much. Thank you for your time.
Thank you.
So I have just a quick question for you, if my colleagues will allow me. So, did you have the chance to do any cost estimation of the implementation of the project?
Yeah.
Because you've got part software, you've used boards, you've
Yeah. So for me, the actual robot, everything together cost 1,000.
1,000.
Yeah. We can reduce it with like 800. And the simulation part in MATLAB was for me. I just downloaded from under the university license, and also the microchip MP lab was. So I downloaded online. I downloaded the trial version, the student version.
Okay, thank you. I got the answer. Would you like to
And
have?
I don't know if I have time to show you the video or
Later on, maybe.
Later on?
Yes, yeah. Because we need to keep the time and.
Sure.
Would you like to?
Okay, Reza, thank you very much. That is a very interesting project as well.
Thank you.
And I see you're dealing with complexity of parameters, you know, and lots of adjustment, you know, for synchronization and so on. Why did you choose the ultrasonic sensors? Why is ultrasonic?
Okay. So in order
It's the frequency, I don't know, is matching with the radar. There are two different frequencies there, you know?
Yeah, for example, we couldn't use the GPS localization because GPS has definitely more errors, because the field of the moving robot is just the 2 by 2, 2 meters by 2 meters. So by having 1 meter, error, so we cannot really do that. We need to have very sensitive and very more accurate analysis. So that's why we use the echo position in order to know the location of the robot.
So precision.
And the robot, you don't know what kind of speed is moving, or is unknown?
The speed of the motors is you can adjust with the program that I use. Because we don't have the encoder attached to this one, so I can manually adjust it. It depends on the pulses that you send it to the motors, which controls the speed.
The important thing is to synchronize all those parameters and get the optimum.
Yeah.
Yes.
Okay.
And, okay, good luck.
Thank you very much. I also want to thank you, my supervisor, Dr. Fernando, who supported me and provided me the chance of this opportunity to work on this interesting project.
That's wonderful.
Thank
you.
Question?
I just have a quick question. Your project was based on mining. Well, that's the impression I got. You didn't get that impression? Yeah. Can it be applied to any other industry?
Yeah, actually it is like radar positioning. And for example, as I mentioned, it can be applied to detect or find any objects in the field, and find it and then push it to the other proper locations. Also, for example, in order to move the object from the path for the safety, as I mentioned.
Okay. Thank you very much, Reza, and thank you for the interesting talk. Thank you.